What I'd like to address now is a little bit about molecules and how molecules are formed and its relationship to chemical bonding. Alright, so let's define molecules. Kind of already did, but basically we said a molecule is a chemical that is composed of two or more atoms. Now these can be the same atoms or they can be different atoms. For example, oxygen is never found as just a single oxygen atom. It's always found as paired with another one. Okay, so we write it as O2. Okay, one instance of oxygen, an oxygen molecule, is two oxygen atoms bonded together. Sodium chloride, two or more atoms. In this case, they are different. Hydrogen, again, is another one of those atoms that we find paired with itself. Okay. In fact, there's a whole group of them. Hunkelbrief. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine all are found paired together when they are single atoms. Well, when we're talking about oxygen or iodine, what have you. They are found paired together. And so all of these would be molecules. One instance of hydrogen here would be a hydrogen molecule. We have two hydrogen atoms bonded together. Sodium chloride, on the other hand, is a molecule, but yet in this case it's two different atoms joined together. Compounds, on the other hand, are molecules that are two or more different atoms bonded together. Always going to be two or more different atoms bonded together. So while we can have a molecule of carbon dioxide, okay, a molecule is one instance, the compound itself is carbon dioxide. Glucose is a compound. But if we have one instance of glucose, or one sample of glucose, C6H12O6, that would be a molecule of glucose. 6 carbons, 12 hydrogens, and 6 oxygens. Let's talk a little bit about some what we call formulas here. When we talk about a molecular formula of an atom, or excuse me, of a molecule, we're talking about the number of atoms and the type. So if we look at our example here, we look at ethanol. Should be a line here. If we look at ethanol, the molecular formula for ethanol is C2H6O, meaning that it has 2 carbons, 6 hydrogens, and 1 oxygen. Look at ethyl ether. Well, we'll get back to that. So the molecular formula only tells you the number of atoms and what type of atoms are present in that particular molecule. If you want to know how those atoms are arranged, you have to look at what we call the structural formula. This shows you the organization of those molecules and the exact relationship between the different atoms. For example, look at ethanol and look at this ethyl ether. They have the same molecular formula, however, look at the structural formula. Notice that the difference is that this oxygen is found between the 2 carbon atoms, whereas up here with ethanol, that oxygen is attached to only 1 carbon and it has a hydrogen bonded to it. Now, we have the same molecular formula, C2H6O. Even though they have the same molecular formula, their structural formula is different. These would be called structural isomers. Meaning that they have the same molecular formula, but yet they are structurally different. We see that a lot with other organic molecules such as carbohydrates, which are sugars. C6H12O6 typically is going to represent glucose. However, we can change that around and we can get different sugars with that same molecular formula, or different molecules with that same formula. But typically, the C6H12 is used to represent glucose. Okay, so we have a molecular formula and structural formula that really, in order for you to really understand what the molecule is and what its properties are, you need to know both of those. And then isomers would be when you have molecules with the same molecular formula, but yet their structure is different. All right, let's talk about chemical bonding. There's three main types of chemical bondings I want to address with you. We have ionic bonds, we have covalent bonds, and we have hydrogen bonds. By far, the strongest of those bonds would be covalent bonds, and we'll talk about why those are the strongest. The weakest of all these are hydrogen bonds. All right, let's take a look first at ionic bonds. Ionic bonds are those bonds that form between cations and anions. Or, in other words, the bonds that form between positively charged atoms and negatively charged atoms. Sodium with a positive 1 charge, chlorine with a negative 1 charge, they bond together to form sodium chloride. We know that sodium is going to donate its electron to chlorine to fill up its valence shell in chlorine. Sodium loses that single electron, ends up with a full valence shell in this second orbital here, which is what they want, and then as a result they join together. Okay, so this is basically an opposites attract type of thing. In a way, you can look at it as kind of an electrostatic attraction, these positively charged and negatively charged kind of forming a neutral bond with one another. Okay, second type of bonding, covalent bonding. There's two types. There are what we call polar covalent and nonpolar covalent. And what this polarity refers to is the fact that some electrons, well, let me define covalent bonds for you first. Covalent bonds are where when electrons are shared between atoms. They don't physically donate them, they don't leave the shell, but they are shared, meaning, well, you know that electrons are orbiting the nucleus of the atom. Well, what happens in certain kind of bondings is that those atoms will then take turns rotating around the different atoms. So in the case of hydrogen here, we know that hydrogen always, when we talk about hydrogen, it always comes in pairs. Each hydrogen, because it's hydrogen is atomic number of 1, it's going to have 1 proton and 1 electron. Well, that first electron orbital we know only holds 2 electrons. Well, this valence orbital is not full. It's going to need a second one. So hydrogen will join with another hydrogen atom, which also needs a second one. And by joining together and by sharing those electrons, meaning both of those electrons are going to rotate equally around. Equally is kind of a key term here. They're going to rotate equally around both the nuclei of both of those hydrogen atoms. Same works down here with carbon dioxide. We have, it's a little more complex, but basically what's happening here is that oxygen with atomic number of 8, meaning it's going to need 2 electrons in its outer shell, 2 electrons here. Carbon over here, atomic number of 6, it's going to need 4 electrons in its outer shell. Ultimately what happens is you get these electrons kind of rotating like this, and these rotating like this, ultimately then creating a stable valence shell among all these atoms, and as a result they join together and form these bonds. These covalent bonds are very strong. You can't take something covalently bonded and put it in water and it will not dissociate. Ionic bonds, many ionic bonds will do that they're very easy to break. Covalent bonds are not like that. You need you need to put a lot of energy into the molecule to break those bonds. Water will not do that. Alright, let's talk about the difference between polar and nonpolar covalent bonds. Polar and nonpolar. Let's talk about nonpolar first, right here. Nonpolar covalent bonds means that there's an equal sharing of electrons between those atoms, meaning that those electrons that are being shared will spend an equal amount of time rotating around the nucleus of those different atoms. Polar covalent bonds mean that there is an unequal sharing of electrons between the atoms. What that means is that one of those electrons will spend more time around one atom as opposed to the other. Let's look at water, for instance. Water has an oxygen and two hydrogens bonded together. Oxygen has an atomic number of 8. It needs 2 more electrons in its valence shell. Hydrogen needs 1 electron in its valence shell. And what we end up getting is that 1 electron from this hydrogen and 1 electron from this hydrogen, both will then spend more time rotating around this oxygen than they will around the hydrogen. As a result, what we get is the location of the molecule where the electrons are spending more time ends up with a slightly negative charge. The area where the electrons are not spending as much time ends up with a slightly negative charge. And that's what this little Greek, I believe that's a Greek gamma, represents. That this has a slight negative charge, this has a slight positive charge. And it creates this polarity, meaning like a battery. It has polarity. It has a positive pole and a negative pole. The Earth is polar. It has a north pole and a south pole, and has to do with magnetics and electromagnetism. It's the same idea. A couple interesting things. Polar covalent molecules will dissolve in water. Nonpolar covalent molecules are insoluble in water. Lipids, or fats, oils, are made of nonpolar covalent bonds. They will not dissolve in water. You can add oil to water. What does it do? It floats at the top. You can shake it up and form these little tiny drops, and eventually those fats will then kind of coalesce and go back to the top and form this big sheen, this big layer of fat on top. That's because of those polar covalent bonds. Excuse me, nonpolar covalent bonds. Things that are polar covalent will dissolve in water because water, as I just gave you the example before, water is made of polar covalent bonds, slightly positive charge around the hydrogen, slightly negative charge around the oxygen. And so because of those slight charge differences in the molecules, they then are able to dissolve, because what you get is slightly negative and positive attractions between the slightly positive negative parts of the molecule. Third type of bond I want to address are hydrogen bonds. And these are very, very weak bonds. They are not permanent bonds. I like to say that they're fleeting. They don't last very long. And the best example we can find of hydrogen bonds to show is in water. We know water molecules have slightly negative charge around the oxygen, slightly positive around the hydrogen. And what we see is that the slightly positive end of one water molecule will be attracted to the slightly negative end of another molecule and form these very, very weak bonds. And those bonds can break very easily. In fact, one of the things you should understand is that atoms and molecules are constantly in motion. Water is no exceptions. Even if you have a glass of water on a counter that's perfectly still, the atoms and molecules in there are constantly in motion. And so what we're getting then is we're getting the formation of these hydrogen bonds and the breaking of these hydrogen bonds very rapidly all the time. Let me show you this video here hydrogen bonds are and its relationship to polar covalent bonds. So there's our water molecule. The charged ends, slightly positive, slightly negative. And kind of like two strangers passing in the night, making eye contact, they form this brief instant bond to one another, and then they move on and pass each other in the night and don't see each other anymore. Kind of the way with hydrogen bonds. It's kind of a good analogy, I think.